Okay, welcome back, everybody. We're going to move through chapter 3 now, and we're going to do it in sort of an out of order fashion, but we're going to try to move this chapter along a little bit quicker than normal. Of course, this is Math 235 still, and a lot of the things in probability due to time constraints we're not going to focus too much on, in particular things like finding theoretical probabilities. So we're going to handle all of chapter 3 in one set of lecture slides here, and our first goal is going to be just to understand some basic notation and notions in probability, including what a sample space is, what an event is, and what the definition of a probability of an event occurring is. And so a quick word before we go on. Why do we study probability in the statistics course? And the answer is that the key to understanding data rests, and making proper conclusions on it, rests in a large part on probability. And in particular, we need to understand how likely things are to occur in order to make the right types of conclusions that we'll ultimately want to make. And so what I mean by that is, as a quick fun example, let's suppose that we were doing a statistical study where I gave a drug to pregnant women, and my claim or my feeling was that this drug would somehow increase the likelihood that a child being born is a girl. And we'll assume for now that when a parent has a child, that the likelihood of that child being a girl is 50-50, right? We have a 50% chance or a 1 in 2 chance that the child will be a girl, and of course a 1 in 2 chance that the child will be born a male. So let's suppose that in my clinical trial I give 100 pregnant women this drug, and 97 of them gave birth to females. What would you conclude about your drug? Was it effective or not? How do you analyze this data properly? So, in general, of course, you've heard this phrase before, correlation does not imply causation. So, just because there's seemingly a clear correlation between the women who have taken my drug and the women who have female children, that doesn't necessarily mean that the effect was caused by my drug. And in particular, any cause that I see, any correlation that I see, there is a shot, there is a chance that this was an occurrence of chance. So what are the odds that if I had 100 women and my drug didn't work at all, that 97 of those 100 would give birth to females? I need to understand these numbers, and this is a question of probability, in order to correctly understand if I've really witnessed an effect from my drug. So what are the odds that 97 of 100 women gave birth to girls if there was no factor of my drug? And I can tell you what this is. This isn't too hard to calculate, but I'll show you how we calculate things like this as we go forward. But if I told you, and you'll take my word for it now, that the probability of 97 out of 100 women giving birth to females is 1 in this number, 1 in 126 zillion, or whatever that comes out to be, then we at least get an intuitive idea that what we saw was overwhelmingly likely that it was not due to chance. And then what I conclude is that my drug probably did have some effect. So let's talk about some basic notation first. In probability, we deal with procedures which produce some sort of outcome, and we call these probability experiments. So an easy example might be something like a probability experiment could be just the tossing of a coin once. I toss a coin once. This produces some sort of outcome. In particular, the outcome is known as either heads or tails, depending on how the coin lands. That's what a probability experiment is. A particular result of one trial, I could toss a coin multiple times. So each time I toss that coin, I can call it a trial. The result of one trial is called an outcome. So in this particular example, my outcomes are heads or tails, and I'll always denote heads with just an H to save me from having to write it over and over, and we'll denote tails with just a T when it's clear what that means. And the set of all possible outcomes, if I take every outcome that I could possibly have in my experiment and I write it in nice little curly brackets, these are set notation brackets, then this is a set called the sample space. It just consists of all possible outcomes. And there's some criteria for this to be a sample space. It does need to consist of every possible outcome. And we also need to make sure that all of the outcomes in our sample space have the same chance of happening, right? We assume that there's the same chance of me getting either heads or tails in this experiment. And so as another example, one with a little bit of a bigger sample space, I can think about just rolling an ordinary dice once. A dice having a six-sided die in this particular case. I roll the dice once, that's my experiment. My sample space here would consist of all the possible outcomes that I could get when I roll this die. I could get either a 1, 2, 3, 4, 5, or 6. And one possible outcome in my little experiment might be that I roll a 5, right? Of course, I could roll any other number as well. And oftentimes it's the case that I'm not interested in just one particular outcome of my sample space, but I might be interested in the likelihood of any number of several outcomes sort of combined together occurring. So for instance, I might just not be worried about this outcome. I might be worried about something like what are the odds, or what is the probability that I roll an odd number? What's the probability that I roll a prime number? What's the probability that I roll a 6 or a 2 or something to that effect? And so when I collect multiple outcomes, a subset of my sample space together, we call this an event. So the event would be rolling an odd number, or the event could be rolling a 6 or a 2 or whatever. And so I can always express an event as just a subset of the sample space. Here 1, 3, and 5 is a subset of the bigger sample space 1, 2, 3, 4, 6. So for example, we can do a quick example here. If I toss a coin 3 times, that means I take my coin once, I toss it, I get either heads or tails. Then whatever happens, I'm going to toss it again, and I'll get either heads or tails again, and then I'm going to repeat this a 3rd time. Try to write out the sample space for this particular experiment in sample space in set notation, and tell me which set would describe the event. I've tossed exactly 2 heads in my 3 tosses. So how did you do? Well, what would the sample space be? One way to come up with these sample spaces, sort of what I was drawing here, is called a probability tree. If I have sort of a separate trials of my experiment happening over and over, kind of running out of space here, I can think about each of these trials as being sort of a branch in this tree. And so on my first occurrence, I could have either got heads or tails. Suppose I got heads. And then on my second toss, I would have got either heads or tails again. Maybe I got tails. And on my 3rd toss, I might have got heads or whatever. And I can think about this branch as representing the set of all possible outcomes, right? Or this tree, sorry. So any way that I can traverse through this tree is going to lead me to a different possible outcome. Here in green would signify me getting tails and then heads and then tails. In blue, I'm getting heads and then tails and then heads. So if I want to express all the possible outcomes in my probability experiment, I could look at just the outcomes that come out at the end of my probability tree. And in this case, it looks like I have exactly 8. I could either toss heads, heads, and heads. I could either toss heads, heads, and tails, heads, tails, and heads, heads, tails, and tails, and so on and so on. And this represents all the possible ways that I could possibly write down some combination of an H and a T in this format, where I have 3 letters together. And so this is my sample space. And notice how, in theory, I have the same chance of any of these events occurring, right? I'm no more likely to get 3 heads as I am 3 tails. And I'm, in fact, no more likely to get 3 heads as I am to get a head, a tail, and then a tail in that order. So back to our original question, which subset of this set of 8 total outcomes would describe the event where exactly 2 heads are tossed? Well, the answer is just look at my sample space and tell me which of these involves me tossing exactly 2 heads. And it's easy enough to see it doesn't include this because here I have 3 heads. Since I said exactly 2 heads, that doesn't count. Here I've tossed 2 heads and a tail. Here I've also tossed 2 heads and a tail, just in a different order, and here as well, right? So in this particular case, there's 3 different ways that I could toss 2 heads exactly. And so the event would be this little set here, right? HHT, HTH, and THH. And remember, the whole idea is that this has to be a subset of my sample space right here. Okay, and so what's our definition of probability? The theoretical probability, there's another type of probability called statistical probability, so we'll make that distinction for now. of an event E happening is the size of E divided by the size of S. And so the way we think about this is it's the number of ways that E could have occurred. And so in our example, E was the event of tossing 2 heads. How many ways could I have tossed 2 heads in this experiment? The answer was 3. I could have tossed heads, heads, tails, heads, tails, heads, or heads, or tails, heads, heads. There was 3 ways that E could have occurred. 1, 2, 3. And how many ways could anything have happened? What was the size of my sample space? Well, remember we already found that there was 8 total outcomes. So the total number of outcomes was 8. The number of outcomes in my event was 3. So I find this probability to be 3 over 8. Okay, and one final note before we go ahead and do an example and finish this video off. The probability that you get should always be less than 1, and it should always be positive. There's no, if you look at the definition of our probability, the size of both sets is positive, and the number of events is always a subset of the sample space. So that leads to a smaller numerator than the denominator down here. So we should always get a number less than 1. So go ahead and try this question at the bottom. If I take a standard deck, that's 52 cards, where I have hearts, clubs, spades, and diamonds in equal representation. My question is, if I pull a card randomly from this deck, what's the probability that that card comes out as a heart? I try to do these questions by writing out a sample space just for extra practice. Second question, if I pull one card from the deck, then put it back and pull a second card, what's the probability that both cards came out as hearts? Give it a try. Okay, so let's see how you did. So in our first question, our example is we have one card drawn here from the deck, and the question is quite simply, what's the probability that the card that I drew was a heart? And I'm pretty sure a lot of you might have guessed this without even having to think about it too hard. The answer is 1 out of 4, and that is true. And so the way we actually think about this, and it's a good idea when you think about probability to really first think about what the sample space is. So if I'm drawing one card from a deck, there's lots of ways I could actually think about this sample space, but in this case, since I'm only concerned with the suit, the most sensible sample space is hearts, clubs, spades, and diamonds, right? So each of these represents a possible outcome. I have the same likelihood of drawing either a heart, a club, a spade, or a diamond. So this is a fair sample space. And the event of me drawing a heart would just be the one possibility in here. The only way that I could draw a heart is if I pull a heart, and it would be just this H. So to find the probability of this event, the probability of me getting hearts, P bracket, event in the brackets is a notation for probability, would be the size of my event. I only have one possibility in this event divided by the size of my sample space, which is 4. 1 over 4 is 0.25. Or you can write probabilities as percents as well. So I would say I have a 25% chance of pulling a heart, or a 1 in 4 chance. In my second question, the sample space is a little bit bigger because I'm drawing 2 cards. But assuming that I put the card back, I have the same chance of drawing any suit on the second pull as I did on the first pull. So in this case, my sample space is a set of all possible ways that I could take 2 cards from a deck. So if H is hearts, S is spades, and so on, then the sample space consists of pulling hearts first and then hearts second, hearts and then clubs, hearts and then spades, hearts and then diamonds. Pulling hearts first gives me 4 possibilities for the second pull. And then I would have spades and then hearts, spades and then spades, spades and then clubs, and so on and so on and so on. And so how many total ways, if I wrote all of these out, which I didn't, how many different ways would there be to do this? Well, for each of my first card, there's 4 next cards, right? 4, 4, 4, 4, and you can verify yourself that the size of this sample space should be 16 possibilities. So in this case, my event is, I want to consider the likelihood that I'm going to pull hearts twice. So once again, I just have a single event in my sample space, in my event space, and that's a single outcome in my event space, and that's if the event that I pull hearts twice. And so the probability of me pulling a double heart in this case is just 1 out of 16. So that's it for basic probability. Now we'll talk about statistical probability in just a minute.